Well, first I'm going to talk about motivation, a little bit about random close packing, and then mixtures of spheres and sphere cylinders. So, as you might know, with dot particles we can get liquid crystal behavior. This is mainly because of entropy, and there is some work done by Bohos and Frenkel where they study phases of liquid crystal using only sphere cylinders. And well, what is important in this system is the aspect ratio of the sphere cylinders, L over D, with L being the length of the sphere cylinder and D being the diameter of the sphere cylinder. And in this system, what is important for me is that when you have a high aspect ratio, above 10, you start having the liquid crystal behavior at a lower density. So this means that we apply this to colloidal liquid crystals, and this means that with less particles you can have this behavior, liquid crystal behavior. So
Tell me what the vertical axis was.
Sorry. So this is the concentration. It's a normalized concentration, and this is the aspect ratio. Sorry, I did not explain this. So, as I told you, depending on the aspect ratio, you can have only the isotropic phase, the coexistence. This is the nematic, this is the this is the nematic, this is a coexistence. You can have some smectic, this is not the complete, but you can have smectic I, the solid. And this is only just for high aspect ratios. Is that right? Okay. So in our group, what we do is we work with colloidal liquid crystals. So what we do is we put rod-like particles in a solvent. We stabilize these particles. So the particles that we use are clay particles that have a rod-like shape. And what you see here is some TEM pictures of our particles. As you can see, they are really thin and really long. The aspect ratio of our particles is 30-40. It depends on the patch. And what you see here is once we do our suspension, we work with different concentrations, but we choose a concentration. We put the suspension in a cell, and we leave it for a few days until it reaches equilibrium. And what you see here is the consistency between the nematic phase and the isotropic phase. So this is between cross-polarized cells. That's why you see this as a black, because it's the isotropic phase. And this is some previous work. When we compare our results with Frank and Bohos results, we see that in the coexistence we get, this is a different concentration, different units, but this is a concentration. In the coexistence we get lower concentrations for the isotropic phase and higher concentrations for the nematic. This is the data of both Bohos and Frenkel, and the line here that you see just to get the eye. So this difference in the results is mainly because our system is not, it has a high polydispersity of around 40%. And also we say that particles are hard particles, but sometimes we have some kind of interaction that also affects the phase behavior. Another thing that has been done in our group is mixing these suspensions with rod particles, with spheres particles, and the system that we have been studying is of rod particles with an aspect ratio of around 30, and the spheres having a similar diameter to the length of the particles. And depending on the concentration, we can get things like this, where you have domains, a network. You have a network where you have small domains. This will be a domain. So this is a polarized micrograph. What you can see here is the nematic domain surrounded by these dark lines. So we think this is like nematic phases surrounded by the spheres, make it domains and networks. So we haven't studied the phase diagram of this system, and this is one of the things that I'm doing currently in my PhD. So this is just a drum of the possible phase behavior. We haven't totally get to it, but what we expect is some sphere-rich phases, some rod-rich phases, depending on the concentration of the rods and the spheres, and maybe a gel phase at some point. But because we have different things that we can't control in our system, we first want to understand the packing of these mixtures of rods and spheres. So we are not doing liquid crystals for a short period. We are not doing liquid crystals now. Okay, so what I did first was study the random packing of this kind of system, starting by only spheral cylinders and then mixtures of spheral cylinders and spheres. So now I'm going to talk about random plus packing. So what you see here is a picture of M&M's packet. So how can we model this system, random packing? So there are two main ways of doing it. One is sequential generation models, and the other one is collective arrangement models. So in the first one, what you do is you have your box and you just keep adding particles until you can't anymore. And in the second one, you start with a fixed number of particles and a starting dimension of the box, and then you compare the system, move the particles until you can't do it anymore. So what we start doing, we start playing with this system. So at the beginning, we wanted to do something kind of easy. So we start with something similar to a Monte Carlo. And basically, how this works is we always start with an initial configuration, a dilute system, because we don't want to be near the nematic phase. So what we do is, in this case, we compress the system. If we have an overlap, we move the particles. Sorry, we go back to the previous configuration when we didn't have this overlap. We move the particles again, and then we compress. So we could keep doing this until we can't anymore. And well, I'm going to explain this graph. So what you see here, the blue points, triangles are my data. These dark points, these black points are some previous data that I'm going to explain. So this is an algorithm, some results using an algorithm called mechanical contraction method. I'm going to explain later how this works, but the other lines that you see here is just where the nematic and the isotopic phases are. So this is not part of my results. I'm just showing the data of Bolthuis and Frenkel. So my system is not in equilibrium. I'm not having liquid crystal, but I just want to see where this packing sits compared with a nematic phase. So as you can see, I'm starting with only spheres and then going to higher aspect ratios. We have a peak. This is around 0.5 for the aspect ratios. So when we did this, we noticed that we had some kind of order, because when we studied the pair orientation, like when we studied the pair correlation function for the orientation G2, we noticed that we had some kind of order. So what we did next, these are some pictures of configurations. And so what we did then was studying the mechanical contraction method. So basically how this works is that when you have overlapping, for each particle that is overlapping, you find its overlapping particles and the average distance and direction that you need to move these particles in order to get rid of all the overlappings. So, what you do is you think that the particle is moving away with a certain speed, and you calculate the velocities, and this tells you the direction in which you need to move the particles. So you calculate the overlap for each particle and the direction in which you need to move it. So how this works is that you start with an initial configuration, you compress your system, and if you find an overlap, what you do is you do the calculation only for these particles, and you move them, and you keep doing this until you can't anymore. So what happened with this is that when you are close, like for sphere cylinders, not for spheres. When you are close to the maximum packing fraction, it just takes longer because of the orientation, because you have an extra degree of freedom. So what we did was something slightly different. We started using the mechanical contraction method, but once we reached loose packing, we changed to the Monte Carlo-like compression that I was talking about earlier. So what you see here is my previous data using only the compression, and now using the mechanical compression method. So what you see is that I had lower packing fraction, and when we see this with like studying the orientations, we notice that we have less order, because in the previous systems we have some kind of local orientations, local order. Well, this is only the simulations, but what I'm also doing, sorry, some other configuration, but what I'm also doing is doing some experiments. So as I told you, we work with colloidal liquid crystals. So what I have been doing lately is adding some dye to these Rhodes particles in the middle, because the particles that we have channels inside. So I have been adding dye inside, because we want to be able to see these particles using the confocal microscope and to see the liquid crystal behavior, when you add spheres, and also the packing behavior of this kind of system. So at the moment, I have been playing with this system, starting with low concentrations, because we don't want to be near the pneumatic. And we have been putting this in really small capillaries and centrifuging them and seeing how it looks. So what you see here are some pictures of this system. This is between cross polarizers. So what I'm doing here is changing the angle between of the polarizers. So I started with 90 degrees, and this is a change of 30, so the difference is 60, 30, and then 0. So what you can see here is that, well, this is not perfect, this is not what I wanted, because we have some kind of repulsion and some kind of interaction that once we have the sediment, then it starts expanding, and what you see here is liquid crystal droplets. But what you can see in the middle is that we have some kind of, it's not random, but it's not exactly a liquid crystal. So what we are working on is like reducing this kind of interaction. I'm working on doing a better rods, like trying to get rid of all the interaction that I can. So talking about mixtures, so what we did was, now that I had my algorithm for random packing, we start working with mixtures of sphere and rods. The system that we're studying is with really thin rods and big spheres, but I just started, and so as I told you, we want to know where this packing sits in this phase. Well, because with these rods at certain concentration, like they have a gel phase. So, and also with the spheres you have a gel phase. So what we're expecting for mixtures is to have at some point a gel phase. We don't really know this. We are just speculating. And so what I did first was this random packing, but with an aspect ratio of 5. So the rods are not as thin as in a real system. So what I'm showing here is using the same algorithm that I already explained. I'm showing this, the packing fraction. In this axis I had the packing fraction of the sphere cylinders and the packing fraction of the spheres. So I did different concentrations of spheres and sphere cylinders. And so in this point you have only sphere cylinders, and here you have only spheres. And as you change, like as you mix it, you get this behavior. It's kind of aligned, but it's not exactly aligned. So I'm plotting this, the same data, but in a slightly different way. So this is the volume fraction of sphere cylinders. This is the volume fraction, the volume of sphere cylinders divided by the volume of the box. And this is the total volume fraction. So as you can see, we have a maximum packing fraction depending for a certain concentration of rods and spheres. So this is what I have until now, but we want to do this now for a higher aspect ratio, 20 and 30, because that's the system that we have. And also we want to carry on with experiments. Now it seems that I have better rods, so we want to start looking at mixtures and play with the packing and also see the liquid crystal behavior and the phase behavior. So, well, these are some pictures of the configurations again. This is only the spheres, just so you can see that they are like equally distributed. Well, it might be the angle, but they are like everywhere. Okay, so thanks to my supervisor, John Panton-Neville at the University of Bristol, to my sponsor, and you for listening.
Thank you. We have time for questions.
I have a question to first part. You were talking about random packing. How you know that it's random besides common? What's the definition? Random packing.
Yeah. So we want something that doesn't have.
Not pneumatic, it doesn't mean random. There are some more sophisticated correlations.
Sorry.
Liquid, it's also random. What means random packing?
Yeah. So we want the highest packing fraction with the less order that we can get. So.
No, I think the question is how you define random packing.
What does it mean, the random?
What do you mean by random packing?
Okay. So it's not order. And the highest
order, what does it mean? That no pneumatic order or something?
She just compresses it.
Yeah, it's not in equilibrium. Just compress it and just.
Not equilibrium to begin with.
Yeah, it's not in equilibrium.
But might be there are some more sophisticated correlations. What the?
No, there's not. There's not. So there has been some work on this with the spheres, and they are talking about random packing being related to the glass transition, but there's not like a fixed definition. Basically, what we look is just for not order and the highest packing fraction that you can get. Also, there are different values for this packing fraction because people do it in different ways. So the value that you get, it's not the same because
Yeah, the question maybe is, do you measure the randomness of your packing?
Yeah. So what I look at is that
it would be nice, but how?
Exactly.
So what we look at is at the correlation, like the pair distribution function, and you
Absolutely.
But but. You can be looking at it in different ways, and you can get different values depending on your algorithm. So we have an idea of what we want. It's not fixed. So.
How many particles, by the way?
So I work like with depending on the box and in mixtures, but it's like between 1,000 and 2,000 particles.
Any other questions? Yes.
Yeah, this phase diagram that you draw. You say that. That is not known, but is it not known experimentally? I mean, do you
No, not for this system, not for these big spheres and really thin rods. Yeah, no, it's not known.
And is there also a related question? Is that have people done any kind of mean field theory to basically find out the phase diagram? Do you know?
No, there has been. Well, I know there is some work with using phased function theory with like infinitely thin rods and spheres, but that's the only thing that I know that is has been made.
I have a related question to this phase diagram and to the first picture you showed actually, but let's see this phase diagram.
I do mean with the.
No, just.
Okay, sorry.
With the one you had, yes. So it's clear this is the sphere and the rod reach phases, and there is some in the rods you expect to be pneumatic, and then there is some consistence region. What I don't understand, and the gel is some dynamically arrested phase, which you start off by putting in the one phase region anyway. But why do you expect it to stop there? I would expect this gel or dynamically arrested phase to go all the way following, in the two phase region.
Well, we don't really know how it is. It's just a picture. We think that we might get this. But
why would the dynamics be unjammed here in the bottom? Why doesn't the gel phase go all the way down?
Oh, well, we don't know. This is just a draw. We don't really know. This is what my supervisor thinks is going to happen. I don't quite understand why he thinks that.
And there was a very nice picture at the beginning. Now you can go to the beginning. You know, the rods and the spheres where you have the polarizing microscopy, and you see some nematically aligned. Yes, that one.
Yeah.
That one. If the diameters of the spheres are the size of the rods, is this cartoon?
Yeah, it's not accurate. No, it's just a cartoon here.
But on the other hand, if you look at the picture,
Yeah.
the boundaries between the nematic phase seem to be very thin.
Yeah. So we don't really. This is the only picture that we have for this system. That's why I'm interested in keeping with this work. We want to see again if we get this.
You get from the experiments.
Yeah. So what?
Frame boundaries or whatever.
Well,
They look very thin. Maybe it's just an optical. An optical.
We will need to do this again, but this is the only picture, so I need to do it and
You
see.
don't have quantitative.
No, because it's not. It doesn't have a good resolution.
Okay, that's what I thought. Any other questions? Well, we're on time, so I think we'll move on to the third talk, which is actually not the third talk.